Imagine for a second that you're building a new house.
I see.
Right. But instead of framing it out with wood, laying down bricks, bringing in like modular cabinets, you decide to build the entire thing in one go.
Oh, wow.
Yeah, the foundation, the walls, the roof, even the kitchen island. Just
Okay.
one single massive continuous pour of concrete.
That sounds structurally terrifying.
Right. Because if you find just one tiny air bubble in the living room wall, or, if the concrete doesn't set perfectly in the bathroom, you can't just fix that one room.
You'd have to tear the whole thing down.
Exactly. You have to demolish the entire house and start completely over. It's incredibly high risk. But for decades, that massive monolithic block of concrete is essentially how the tech industry has been building the computer chips that run our entire world.
It really is. It's wild to think about.
It is. So welcome to today's deep dive. We are dissecting Jawad Nasrullah's insider account of the Open Chiplet Economy and really digging into why the era of that monolithic microchip is officially dead.
Yeah, we're looking at a massive invisible shift happening inside the technology we use every single day. And, Nasrullah was actually in the trenches driving this shift.
Which is what makes his perspective so great.
Exactly. It gives us this ground level view of how we're moving away from the single massive silicon chip and entering this entirely new open ecosystem.
So our mission today for you listening is to really understand why this architectural leap was inevitable, right? The intense engineering making it possible, and why it's fundamentally rewriting the rules of global tech design.
It's a huge topic.
It really is. Okay, let's unpack this. We have to start at the catalyst for this change, because that monolithic concrete house method, it actually worked incredibly well for a very long time.
It did. I mean, it was the gold standard.
Right. In fact, Nasrullah brings up a fundamental engineering rule right out of the gate, which is if a monolithic solution works, it should always be your first choice.
Yeah, theoretically, it's the most power-efficient, latency-free way to build a system.
Because everything is happening on one contiguous atomic lattice. There's no gaps.
Right, exactly. For decades, monolithic integration was the undisputed king because the economics of Moore's law just made it foolproof. We could, continually shrink logic gates and pack more processing power onto a single piece of silicon.
But then we hit a wall.
A massive wall. Traditional chip manufacturing started breaking under the weight of modern demands because of two colliding forces. We basically hit the physical limits of transistor scaling just as the global demand for computing completely exploded.
Right. We're asking our hardware to handle workloads today, like hyperscale, cloud computing, neural network training.
Things that require a scale of processing power that just breaks the traditional manufacturing model.
Because we are physically slamming into what are called reticle limits. And for you listening, a reticle limit isn't just like a suggestion. It is the absolute physical size constraint of the lithography machines that print these chips.
Yeah, the extreme ultraviolet machines.
Right. The optical lenses can only project a pattern over a specific square area of silicon. You literally cannot print a chip larger than that footprint. It's a hard stop.
And what's fascinating here is when you combine that hard physical ceiling with a market demanding massively more powerful systems, you face a terrifying economic reality.
The yields just plummet.
Exactly.
Yeah.
The larger you make a monolithic die to try and cram more performance into it, the closer you get to that reticle limit, and your yield drops exponentially.
It's the economics of failure. Like, if a random microscopic speck of dust lands on a tiny component during manufacturing, you throw away, what, a $2 piece of silicon?
Yeah, a couple bucks, no big deal.
But if that same defect happens on a massive reticle limit-pushing monolithic system on chip, you're throwing away a $1,000 processor.
The larger the concrete pour, the higher the mathematical probability that a random defect ruins the whole structure.
Which brings us to the origin story Nasrullah lays out. The year is 2014. Jawad Nasrullah and Ming Zhang found a startup called zGlue in a garage in Palo Alto.
Yeah, 2014. And the word chiplet was practically a foreign language in the commercial industry at that time.
Even though, the concept wasn't entirely new to academia, Nasrullah notes he first heard the term from a Stanford professor around 2010.
Right. The academic world was already modeling this architectural idea of decomposing a chip into smaller functional units.
But modeling it and building it are two very different things.
Completely different. What's fascinating here is the massive gulf between a theoretical model discussed in a Stanford lecture hall and actually shipping a viable product in the hyper-competitive semiconductor industry.
Because zGlue was proposing taking that giant, impossible-to-move block of concrete and replacing it with Lego
Yeah,
bricks.
they wanted to make silicon modular and composable. The vision was to build massive computing systems by snapping together smaller, high-yield, reusable blocks of silicon.
Well, wait, hold on. If the multi-billion-dollar semiconductor industry was entirely optimized for monolithic systems on chip, I mean, trying to force them to adopt a module system sounds like financial suicide for a garage startup.
Oh, it was a massive uphill battle.
Right. The entire supply chain, the testing facilities, the software, it all assumed a single company was designing a single die. Why trying to boil the ocean?
Well, the pushback zGlue faced from established players in 2014 sounded exactly like that. Everyone thought it was a wildly inefficient, unnecessary complication.
But they kept going anyway.
They did, because the founders saw that the need for heterogeneous integration was going to force the industry's hand, regardless of how painful the transition would be.
Okay, let's break down heterogeneous integration because this is where the Lego metaphor kind of starts to fall short and the real physics problems begin.
Yeah, it's not quite as simple as snapping plastic bricks together.
Right. Modern systems require mixing fundamentally different technologies. You need pure digital logic, you need analog signals, you need radio frequencies for Wi-Fi or 5G.
And you need high bandwidth memory.
Exactly. And trying to bake all of those different highly specialized technologies into one single monolithic silicon recipe is just a nightmare.
It really is. Because logic gates want to be built on the newest, most expensive, cutting-edge manufacturing node.
Like 3 nanometer or whatever.
Exactly. But analog and radio frequency components, they don't benefit from shrinking in the same way. They actually perform better and are far cheaper to build on older, larger manufacturing nodes.
So you're paying a massive premium to print analog sensors on a cutting-edge logic process just so they can sit on the same piece of silicon.
It's incredibly wasteful. So splitting them up into separate, specialized chiplets really becomes the only logical path.
But the problem is the packaging, right? Like, we should introduce a more accurate way to visualize this. Moving data across a single monolithic chip is like walking across a room.
Fast. Takes very little energy. Simple pathway.
Yeah. But moving data between two physically separate chiplets is like trying to move millions of people between two massive skyscrapers.
That's a great way to put it. You can't just let them walk. You have to build high-speed, high-bandwidth fiber optic rail lines between those buildings.
And doing that at a microscopic scale is terrifyingly complex. We aren't just talking about gluing two chips to a piece of plastic.
No, not at all. We're talking about advanced heterogeneous packaging. You have to align thousands of microscopic copper pillars between the silicon dies and the substrate below them.
Thousands of them, and they have to match up perfectly.
Perfectly. And then you also have to manage the thermal dynamics. Like, if the logic chiplet runs significantly hotter than the memory chiplet sitting right next to it, the substrate material underneath them expands unevenly.
Oh, wow. So they literally bend.
Yeah, it warps. And that warping can physically shear off those microscopic copper connections, just destroying the entire system.
That is insane. So zGlue wasn't just proposing a new chip. They had to invent missing pieces of this whole packaging ecosystem from scratch.
They needed a silicon integration platform and entirely new multi-die design tools just to manage those thermal and electromagnetic challenges.
It's just an immense physics challenge. But, okay, even if you solve the physics of the transit system between the skyscrapers, you run into an even bigger logistical nightmare.
The standardization issue.
Right. If you want a thriving marketplace where Company A's memory chiplet can talk to Company B's logic chiplet, they both need to use the exact same transit protocols.
And a startup in a garage can't exactly force Apple, Intel, and TSMC to use their proprietary connections.
No, definitely not.
So you need an open ecosystem to force industry-wide consensus. And Nasrullah details a major turning point here in 2019.
The launch of the Open Chiplet Economy project.
Exactly. Within the Open Compute project, originally called ODSA, the goal was to create the foundational bumps and grooves that would allow this modular marketplace to actually exist.
Here's where it gets really interesting. This project brought together hyperscalers, the massive cloud computing companies who were desperate for this hardware, along with semiconductor firms and system architects.
Yeah, and they introduced two critical standards.
Let's talk about the first one. Bunch of wires, or BOW. This wasn't just a corporate agreement, right?
No, it was a physical layer standard that solved the immense power bottleneck of driving signals off die. BOW provided this lightweight, standardized interface for chiplets to communicate across that microscopic gap without just burning through the system's power budget.
Okay, and the second major contribution was CDXML, the chiplet design exchange markup language.
Right. This was the machine-readable language that allowed engineers to actually integrate these discrete blocks.
So it's like a data sheet, but for the software.
Basically, when you buy a chiplet from a third-party vendor, CDXML provides the exact digital passport of that component. Its physical footprint, its thermal profile, its electrical characteristics, so your design software knows exactly how to handle it.
And these early open standards were the absolute spark. I mean, they paved the way for the massive industry frameworks we see today, like UCIe and 3D blocks.
Yeah, when major players like ARM joined the initiative, it totally validated the entire architecture.
But also triggered a catastrophic disruption to the traditional EDA oligopoly, the electronic design automation software companies.
Oh, yeah. The EDA market had been dominated for decades by a few vendors whose tools were perfectly optimized for monolithic SOX development.
Right, their simulation tools were built to analyze a single continuous silicon substrate.
And chiplets completely broke that computational model. You're suddenly dealing with electromagnetic interference crossing between different dyes, complex thermal bottlenecks in three-dimensional space.
You know, this disruption mirrors exactly what happened with cloud computing.
Oh, that's a good point.
Yeah, cloud computing destroyed the old IT model of buying, racking, and maintaining physical enterprise servers in a basement. It changed the entire abstraction layer.
Right, in the 90s, a systems admin cared about the physical hard drive spinning.
But today, you just provision a functional block of storage in the cloud. You don't care about the disk. And chiplets shift hardware design from transistor-level integration to system-level composition.
Exactly. In the monolithic era, a chip designer was focused on placing specific logic gates to minimize, like, nanoseconds of latency.
Just agonizing over individual transistors.
Yeah, but in the chiplet era, you're operating at a much higher abstraction layer. You're provisioning entire functional blocks, like a 5G modem from one vendor, a neural processing unit from another, advanced memory from a third.
And your job is just architecting the system where they communicate flawlessly. You're conducting the symphony instead of trying to carve every single violin out of wood yourself.
That is exactly it. The companies who win this new era won't necessarily be the ones building the best transistor-level layout tools. The ultimate winners will be the platforms that enable this higher abstraction layer.
Right, providing the software and multi-die verification tools that make reusable building blocks seamless for the architects.
Seamless is the key.
So we have the physics of reticle limits forcing the change. We have the yield economics making it viable. We have the open standards like BOW and CDXML solving the communication bottlenecks. It sounds like a perfect, unstoppable tech triumph. But
physical chips still have to be manufactured in the real world. And Nasrullah's article brings us to a very sobering reality check regarding government bureaucracy, geopolitics, and where these things are actually built.
yeah, as chiplets became a critical strategic technology, governments naturally intervened. And Nasrullah explicitly critiques these efforts.
He calls out the DARPA CHIPS program, which was heavily focused on large defense contractors, and the subsequent U.S. Cheap Pieces and Science Act.
Now, we should be clear here that we are specifically exploring Nasrullah's perspective as an insider. We're not taking a side on the politics, just reporting his view from the source text.
Right, absolutely. And he argues that while initiatives like the National Advanced Packaging Manufacturing Program brought a lot of visibility and funding to the space, they failed to produce major commercial breakthroughs.
Nasrullah frames these government efforts as being fundamentally slowed by structural inefficiencies and bureaucracy, which he contrasts heavily with the blistering pace of innovation that was emerging organically through, open, borderless collaboration in the private sector.
Yeah, and he makes a really controversial point here regarding the billions poured into the Cheap PS Act.
The slideware comment.
Exactly. He argues that outside of Asia, we're still largely seeing what he calls slideware, fancy PowerPoint presentations and press releases, rather than large-scale, operational advanced packaging factories.
So if the U.S. is pouring billions into this, why are we still seeing slideware? Why aren't we seeing actual manufacturing capabilities outside of Taiwan?
Well, if we connect this to the bigger picture, it highlights the stark difference between intellectual innovation and entrenched manufacturing infrastructure.
Right. Designing it versus building it?
Exactly. The knowledge to design the Legos, to architect those transit systems between the skyscrapers, is highly distributed.
Yeah.
And it's often led by the U.S.
But the actual physical capability to assemble these complex, heterogeneous packages remains deeply centralized. Right now, Taiwan remains the single dominant manufacturing source for advanced packaging.
And the ecosystem in Taiwan isn't just a collection of factories. It is a deeply entrenched network of substrate suppliers, testing facilities, specialized chemical vendors.
They've been doing this for a long time.
Over a decade, they've been iterating on this specific manufacturing problem, and it creates this severe cultural and supply chain gravity.
So you can't just copy-paste a factory somewhere else.
No. Nasrullah concludes that pure domestic isolationism in manufacturing just isn't practical or realistic right now. The sheer complexity of advanced packaging means global cooperation remains absolutely essential for the chiplet economy to function.
It's a critical geopolitical bottleneck for sure. But let's pivot to the application side. We've mapped out how they're built, where they're built, the standards holding them together. So what does this all mean for you listening? Like, where are these modular architectures actually living in the wild today?
Well, the most dramatic and immediate application is the artificial intelligence revolution. AI has pushed the scale and complexity of computing systems far past what a single chip can handle.
Oh, absolutely. I mean, training a modern large language model requires massive compute arrays, high bandwidth memory stacks sitting literally millimeters away from the logic cores.
And advanced networking fabrics pushing terabytes of data. Building that monolithically is physically impossible.
So chiplets are really the foundational enabler of modern AI architecture.
They are. And Nasrullah notes a profound architectural inversion happening in these high-end AI systems. Basically, the chip package itself is essentially becoming the new system board.
The package swallowed the motherboard.
Exactly. Instead of plugging components into a massive green motherboard like we used to, all of those separate functional blocks are being heterogeneously integrated onto a single advanced packaging substrate.
That is a wild paradigm shift. But AI data centers, they represent the bleeding edge of performance. Nasrullah also points to the complete opposite end of the spectrum, what he calls the long tail of computing.
Right, we're talking about robotics, automotive systems, smart industrial automation, edge devices.
So why does my smart thermostat or my car care about this? I get why a massive AI data center needs chiplets, but why the long tail?
The long tail cares about chiplets for a completely different reason: cost and customization. It's the economics of high-mix, low-volume silicon.
High mix, low volume. Give me an example of that.
Okay, think about a company designing a specialized braking system for a specific model of an electric vehicle. They might only need to manufacture, say, 100,000 units a year.
Which sounds like a lot, but in silicon terms.
In silicon terms, designing a custom monolithic system on chip for a volume of 100,000 units is economic suicide.
Because of the NRE, right, the non-recurring engineering cost.
Exactly. The tens of millions of dollars you spend designing, simulating, and tooling the masks before you ever print a single chip.
It's just too high. Traditional SOX economics demand production runs in the tens of millions, like smartphone processors, just to amortize that upfront cost. You can't justify the architectural blueprints for a custom concrete mansion if you only need to build a few small garden sheds.
Which is exactly where the Open Chiplet marketplace changes the game. That electric vehicle manufacturer. They can simply buy a standardized logic chiplet off the shelf.
Oh, I see.
Pair it with the standardized memory chiplet, design their own highly specialized sensor chiplet, and package them all together using standard BOE interfaces.
So it provides a highly customizable, practical alternative that completely slashes the upfront engineering costs.
It completely democratizes hardware design, allowing advanced, specialized computing to spread into that long tail of everyday devices.
Let's take a step back and look at the velocity of this transition. Because the timeline Nasrullah maps out is staggering for an industry built on billion-dollar hardware cycles.
It really is. The semiconductor industry completely inverted its core architectural philosophy in barely over a decade.
Yeah, think about it. Around 2010, the chiplet is merely a theoretical concept circulating in Stanford academic papers. By 2014, zGlue is in a Palo Alto garage trying to productize heterogeneous packaging while facing immense skepticism from an industry addicted to monolithic scaling.
And then by 2019, the physics basically demand a change. The Open Chiplet Economy is launched, and standards like BOW and CDXML create the standardized bumps and grooves for the marketplace.
And today, as we look toward 2030, chiplets are the absolute bedrock of both the hyperscale AI revolution and the specialized edge computing market.
This raises an important question, though, a thought to leave you with, building on the trajectory we've explored today.
What's that?
Well, if the chip package is literally becoming the new system board, and if hardware design is moving toward this highly modular drag-and-drop composability, Will the future of hardware engineering eventually become completely indistinguishable from software programming?
Oh, wow. Will hardware architects eventually just pull specialized chiplet libraries from a marketplace, drop them onto a digital canvas, and literally hit compile?
It's entirely possible.
And if hardware design does become that purely abstract and democratized, the physical reality still remains. Who will hold the ultimate power if the global capability to actually manufacture and assemble those physical blocks remains entirely centralized in Taiwan?
It is a massive engineering triumph, wrapped in an unresolved geopolitical puzzle.
It really is. Well, we want to thank you so much for joining us on this deep dive. Hopefully, the next time you hear about a breakthrough in AI or a new smart automotive system, you won't picture a single solid brain of silicon, but a brilliant, ever-evolving team of specialized blocks working in perfect unison. Stay curious, and we'll catch you on the next deep dive.